Welcome back to the video lecture series of Digital Fundamental. Today we will discuss synchronous up and down counter. So let's start with the definition of synchronous counter and up and down counter. So this synchronous counter is basically a group of flip-flop in which all flip-flops receive same external clock signal. Okay, this synchronous counter is basically a counter in which we have a flip-flops and all flip-flops receive same kind of external clock signals, and this up and down counter is basically a combination of up counter and down counter. That means it counts either in upward directions or in a downward directions depending on our requirement. Okay, here we have this up and down counter means we have either small to large count or large to small count. Okay, this up and down counter is basically a combination of up counter and down counter, and to design and bit synchronous up and down counter we have to use and flip-flops having same clock signal. Okay, to design and bit synchronous up and down counter we have to use and flip-flops having same clock signal. As this synchronous counters have a same external clock signals, that's why this synchronous counter is known as parallel counter. This counter is also known as parallel counter because all flip-flops receive same external clock signal. So all flip-flops will work parallelly. All flip-flops will be triggered at the same time. Okay, that's why this synchronous counter is also known as parallel counter. And here in this synchronous up and down counter we have to apply inputs to operate in a desired manner. Okay, so here in a synchronous up and down counter we have to apply flip-flops input, but this all flip-flops have a same external clock signal. So whenever we want our desired sequence for this up and down, so we have to apply our input combinations into the flip-flops. And here in this synchronous up and down counter our flip-flops will work in this toggle mode or not. It depends on flip-flops input only. Okay, here in this synchronous up and down counter if we apply inputs and our flip-flops will work in a toggle mode or not, it depends on flip-flops inputs only. Now whenever we want to design this synchronous up and down counter we have to design a counter which counts either in a upward directions or in a downward direction depending on our requirement. So here to count in either upward directions or in a downward directions we have to use one mode signal. Okay, so in a synchronous up and down counter we have to use one mode signal, that is M, to count either in a upward directions or in a downward directions. Now in this synchronous up and down counter, this synchronous up and down counter works as up counter whenever we have a M is equals to 1. Okay, whenever this M is equals to 1 we have a synchronous up counter sequence. That means it counts in a upward direction small to large when we have a M is equals to 1. Okay, and if we have a M is equals to 0 then this synchronous up and down counter will work as a synchronous down counter and it counts in a downward directions. So here using this one mode signal we can apply input combinations, and according to that we have our output characteristics either in upward directions or in a downward directions. So let's discuss this synchronous up and down counter with example. Here we have a 3-bit synchronous up and down counter. So to calculate either in a upward directions or in a downward directions, we have to first check out both the counting, that is up counting and down counting sequence. So here we have a first up counting sequence which count in a upward directions like 0, 1, 2, 3, 4, 5, 6, 7. Here we have a 3-bit synchronous up and down counter. That means using 3 flip-flops we can count total 2 raised to 3. That means total 0 to 7 values. Okay. So here we have this 7. Then again our counter will restart. Okay. So here again we have a 0, 1, 2, 3 and so on. Okay. So to design this kind of up counter, we have to check out flip-flops input. So here we have our desired output sequence, and if we want this kind of output sequence, we have to apply input according to that. Okay. So first observe all the output combinations and according to that apply inputs to the flip-flops. Okay. So here in a Q1 we have this toggle mode operations. That means for a first flip-flops it must be in a toggle mode. Okay. So we have to apply input like up counting like this, J1 K1 is equals to 1. For up counting we have a J1 K1 is equals to 1 whenever we want output for Q1 like this. Okay. Now for next Q2, here this Q2 will change its state whenever we have a Q1 is equals to 1. Okay. So whenever Q1 is equals to 1, we have a change of states such that here we have a toggle mode operation. So we can connect this J2 K2 is equals to Q1 for up counting sequence of this Q2. Okay. So here we have a J2 K2 is equals to Q1. So because whenever Q1 is equals to 1, we have a change of state. That means basically toggle mode operations. Okay. So this is for a Q2 sequence. Now whenever this Q3 will toggle its state when Q1 and Q2 both are equal to 1. Okay. If Q1 and Q2 both are equal to 1, we have a change of states. So here we have this J3 K3 is equals to Q1 into Q2. Okay. Because whenever Q1 and Q2 equal to 1, we have a change of its state. Okay. So here we have this input combinations for our up counting. J1 K1 is equals to 1, J2 K2 is equals to Q1 and J3 K3 is equals to Q1 into Q2. So this is for up counting. Now let's discuss for down counting. So here we have a table for down counting. Here in this down counter, this sequence will count in a downward directions. Okay. So here we have a sequence. Initially whenever we have a no clock signal applied, then we have a here 0 0 0. Then when one clock signal applied, we have a 1 1 1. Then we have a 1 1 0. Then we have a 1 0 1 and so on. Okay. So here we have a sequence like 7 6 5 4 3 2 1 0 and again 7. Okay. So this is down counter because it counts starting from this large to small. Okay. Large to small. Now to design this down counter, we have to first find out input value for this. Okay. So to find out input value for this, first observe this Q1. Okay. So for first flip-flop we have to observe Q1. So here in Q1, this Q1 will toggle its states. Okay. Here this Q1 will toggle its states for every clock signal. That's why whenever we have a clock signal applied, we have a toggle mode operations. So for down counting, here we have an input that is J1 K1 is equals to 1. Okay. So for down counting, here we have a first J1 K1 is equals to 1 because here this Q1 will toggle its state for each and every clock signal, and this kind of inputs are applied for toggle mode operation, that is J1 K1 is equals to 1 1. Okay. So this is for
Q1. Now for Q2, here this Q2 will toggle its states whenever we have a Q1 is equals to 0. Okay, whenever Q1 is equals to 0, we have a change of states for Q2. Okay, so whenever Q2 is equals to 0, this Q dash is equals to 1, and for this Q dash is equals to 1, we have a toggle mode operation. That's why here we have a this J2 K2 is equals to Q1 dash. Okay, this J2 K2 is equals to Q1 dash, because whenever Q1 is equals to 0, we have a Q1 dash is equals to 1, and whenever we have a J2 K2 is equals to Q1 dash, so eventually we have a J2 K2 is equals to 1. Okay, so for a J2 K2 is equals to 1, we have a toggle mode operation. That means it change its states whenever we have a Q1 dash is equals to 1. That means we have a Q1 is equals to 0. Okay, so this is how we can find out values for second flip-flop's input using this Q2 output sequence. Now for third flip-flop input, we have to observe this Q3. So this Q3 toggle its states whenever this Q2 and Q1 both are equal to 0. Okay, this Q3 toggle its states whenever this Q1 and Q2 both are equal to 0. So we can say that here in third flip-flops we apply this J3 K3 is equals to Q2 dash into Q1 dash. Okay, here we apply like Q1 dash into Q2 dash, because this third flip-flop will change its states only for the values when both the outputs this Q2 and Q1 are equal to 0. When both the outputs Q2 and Q1 are equal to 0, we have a Q2 dash is equals to 1 and Q1 dash is equals to 1. So basically here in a J3 K3 we have a Q2 dash into Q1 dash. So basically here we have a 1 into 1. So here in J3 K3 we have a 1 as a input, and for 1 as a input we have a toggle mode operations. So here whenever this kind of sequence required for a Q3, we have to apply this kind of inputs into third flip-flop. Okay, so this is here we have a up counting and down counting, and here we have a values for up counting and down counting. For up counting we have to apply J1 K1 is equals to 1, J2 K2 is equals to Q1, J3 K3 is equals to Q1 into Q2, and for down counting we have to apply J1 K1 is equals to 1, J2 K2 is equals to Q1 dash, J3 K3 is equals to Q1 dash into Q2 dash. Now using this two logic we can design up and down counter. Okay, so to find out the values for this up and down counting, we have to make this kind of table. Okay, so here we have this kind of table for up and down counting. Here we write down values of up counting, and here we have a values of input for down counting, and combining this two logic we have a input values for this up and down counting. Now here for up and down counter we have a one mode signal, in which whenever m is equals to 1 we have a up counting, and whenever m is equals to 0 then we have a down counting. So for m is equals to 1, so we can write it simply as a m for up counting, and for m is equals to 0 we can write m dash, that means for down counting. So if we combine all three values, so here we have a up and down counting. So here whenever we have a J1 K1 is equals to 1, because in both the combinations J1 K1 are 1. So here we have a J1 K1 is equals to 1. Now for a J2 K2, here we have a m into Q1 plus m dash into Q1 dash, because when we have this m Q1, so it will count in upward directions. When we have a m dash Q1 dash, so it will count in a downward directions. Okay, so when m is equals to 1 we have a simply Q1, and when m is equals to 0 we have a simply Q1 dash. Okay, so this is how it counts either in a upward directions or in a downward directions. Then here in a J3 K3 we combine this both the values. So here we have a m into Q1 into Q2 plus m dash into q1 dash into q2 dash. So whenever m is equals to 1, this j3 k3 is equals to q1 into q2, so it counts in a upward directions, and when m is equals to 0, this m dash is equals to 1, so basically j3 k3 is equals to q1 dash q2 dash. Okay, so using this kind of logic we can count either in upward directions or in a downward directions, and using this 3 input combinations we can design 3-bit synchronous up and down counter. So here we have a logical diagram of 3-bit synchronous up and down counter. Here we have a 3 flip-flops which has same clock signal. Okay, here we have a 3 flip-flops which has same external clock signal. Here we have a 1 mode signal which is denoted as M. Okay, here we have a this M mode signal, and it has basically 2 lines, this M dash and M. Okay, and here in a first flip-flops we apply input, that is J1 K1 is equals to 1. These values of inputs are which we calculated previously for up and down counting. Okay, so using this equations we can just draw here a logical diagram. Okay, so here in a first flip-flops we have a J1 K1 is equals to 1, so here we apply. Then in a second flip-flop we have a M into Q1 plus M dash into Q1 dash. So here we use this 2 AND gate and 1 OR gate for that operation. So here in a first, here we have a M into Q1 and here we have a M dash, that means it inverted value, and Q1 dash. Okay, so and both the AND gate output is odd over here and it is applied to this J2 and K2. Okay, so this is second flip-flops input, and here in a third flip-flop we have a M into Q1 into Q2, and in a second AND gate here we have a M dash Q1 dash Q2 dash. Okay, and this both the output of AND gate is applied to OR gate, and this output of OR gate is applied to J3 K3. Okay, so using this kind of logical diagram we can count either in upward directions or in a downward directions. Now whenever we have this M is equals to 1, okay, whenever we have a M is equals to 1, then here we have a 1 and this M dash is equals to 0. So if this M is equals to 1, so this AND gate will activated, and here we have this 1 into Q1 and 1 into Q1 into Q1. So in a second flip-flops input we have a Q1, and in a third flip-flop input we have a Q1 into Q2. So it works as synchronous up counter because here we have a input in a such a combinations. Okay, so whenever we have a M is equals to 1, we have a up counting sequence, okay, like this, and whenever we want in a downward direction, so this M is equals to 0. Okay, and when this M is equals to 0, M dash is equals to 1. Okay, so here we have a 1 1, and due to this 2 AND gates will be activated, and here we have a Q1 dash, here we have a Q1 dash into Q2 dash, and because of these input combinations we have a down counter. So this circuit will work as a synchronous down counter whenever we have an input like this combinations. Okay, so this is how we can design synchronous up and down counter. Whenever we have a M is equals to 1, we have to apply input like J1 K1 is equals to 1 for both the combinations. J2 K2 is equals to Q1, J3 K3 is equals to Q1 into Q2. For a down counting we have a M is equals to 0, J1 K1 is equals to 1, J2 K2 is equals to Q1 dash, and J3 K3 is equals to Q1 dash into Q2 dash. So this is how we can design a synchronous up and down counter, and this is how this synchronous up and down counter works. Thank you.